A fan curve shows how airflow changes with the static pressure. The horizontal axis is airflow, usually in CFM or cubic meter per hour. The vertical axis is the static pressure, typically in inches of water or pascals. Each curve represents the fan's performance at a specific speed. As this speed increases, the fan curve moves upward. The system curve, shaped like a parabola, represents the resistance of ducts, filters, coils, diffusers, and other components that restrict the airflow. The point where the fan curve and system curve cross is called the operating point. As filters get dirty and clogged or dampers close, resistance increases. As a result, the system curve shifts to the left and the operating point changes. Now, the fan is providing a smaller airflow than the original operating point. If we want to continue providing the original airflow, then we need to increase the fan speed so that the new system curve crosses the fan curve at the required airflow rate. In fan curves, usually you see a highlighted or gray region on the left side. This region shows where the fan's operation is unstable, and operating point in this region is not desirable. A complete fan curve also shows brake horsepower line, a curve that indicates how much power the fan draws at different points at a given speed, and efficiency curve, a smooth line that peaks where the fan operates most efficiently at a given speed. To read the fan curve, start with your required airflow on the x-axis. Move straight up to the fan curve. The point where you land is the operating point for that fan speed, and the corresponding pressure value shows how much pressure the fan can provide at that airflow. Similarly, you can read the fan's power and efficiency from the overlaid curves. Always aim to select the fan within its stable high-efficiency region. Again, fan performance changes with the speed. According to the fan affinity laws, airflow is directly proportional to fan speed. Static pressure varies with the square of the speed. Power varies with the cube of the speed. In other words, if you double the fan speed, airflow doubles, pressure increases 4 times, and power goes up 8 times. These relationships help engineers predict how fans will perform when speed changes. This video is part of the HVAC Fundamentals course on AEC Learn. If you found this helpful and want to become an HVAC engineer, visit aeclearn.com. And don't forget to subscribe to the AEC Learn channel on YouTube.